The cosmos holds its greatest treasures just out of sight. We gaze at a night sky sparkling with thousands of stars, yet this is merely the visible fringe of a reality so vast it defies comprehension. The most astonishing celestial objects are not in the spotlight. They are hidden in the shadows, veiled by distance, cloaked by cosmic phenomena, or defined by a nature that renders them invisible to our eyes. This is a journey to 30 of those secrets, to the hidden stars you will never see but that absolutely exist. By the end, you will possess a map to the universe's most elusive wonders, a guide to the darkness between the lights. What cosmic phantom, predicted but never glimpsed, could be orbiting our sun right now? What stellar behemoth anchors our galaxy while remaining shrouded in eternal dust? The answers redefine our place in the cosmos. What does it mean to know something is there when you can never truly look upon it? Our journey begins at the very heart of our cosmic home, the Milky Way. In the direction of the constellation Sagittarius, a profound darkness reigns. It is not an empty void, but a monstrous presence hidden by a thick, swirling shroud of cosmic dust and superheated gas. This is Sagittarius, a star, the supermassive black hole anchoring our entire galaxy. You can point a powerful optical telescope directly at its location and see nothing but a murky haze. The light from its immediate vicinity is completely absorbed by that interstellar fog, making it forever invisible to our eyes. Yet we know it is there with absolute certainty because we can witness its immense gravitational hand at work. Astronomers have spent decades tracking the frantic orbits of stars in that central region. They move at impossible speeds, whipping around an unseen focal point like moths around a dark flame. One star, known as S2, completes a single orbit in just 16 years, reaching velocities of over 15 million miles per hour at its closest approach. The only object with enough mass to command such a violent dance is a black hole. Further evidence comes from occasional flares of X-ray and radio energy, the death cries of matter being torn apart just before it crosses the event horizon. The numbers are staggering. This hidden titan contains the mass of over 4 million suns, all compressed into a space smaller than our solar system. It is the silent, invisible king upon whose gravitational throne our galaxy spins. Every star we see at night, including our own sun, is ultimately tracing a path around this central darkness. So the first hidden star on our list is not a star at all in the traditional sense, but the ultimate consequence of stellar collapse, a gravitational singularity cloaked in dust, holding the fabric of our galaxy together from the shadows. From that central galactic darkness, our search for the unseen now turns inward to the very edges of our own solar system. A persistent, unsettling theory suggests our sun may not be alone. It proposes a dim, distant companion, a hidden twin moving silently through the outer dark. Astronomers have nicknamed it Nemesis. The hypothesis emerged from a chilling pattern in Earth's geological record. Roughly every 26 to 30 million years, our planet seems to suffer a catastrophic mass extinction event. Some scientists noticed a potential cosmic trigger. This theoretical nemesis star, they argue, could be a faint red dwarf or even a failed brown dwarf, locked in a vast elliptical orbit far beyond Pluto. Its journey would take it into the frozen reservoir of comets known as the Oort cloud, a spherical shell of icy debris marking the solar system's outermost boundary. Every time Nemesis swings through this distant cloud, its gravity would act like a shepherd disturbing a flock, kicking a shower of comets inward toward the sun. Some of these icy missiles could cross Earth's path with devastating consequences. It is a grand and terrifying idea, a hidden celestial clockwork possibly regulating life and death on our world. Yet for all its narrative power, Nemesis remains a ghost. If it exists, it is an extraordinarily faint object, emitting little light or heat, lost against the crowded backdrop of the Milky Way. Decades of systematic surveys have found no definitive evidence for such a solar companion. The extinction cycle itself is debated, and other explanations, like the solar system's periodic motion through the galactic plane, have been proposed. So Nemesis stands as a monument to a specific kind of hidden star, one born not from observation but from deduction and dread. It is a shadow cast by a pattern, a possible answer to a terrestrial mystery written in stone. Whether it is a real object or a compelling scientific myth, it forces us to confront a profound question. Could our seemingly solitary star harbor a dark, distant partner whose silent, multi-million-year orbit holds a subtle, lethal influence over the history of life itself? The concept of Nemesis presents a hidden star defined by its absence, a cosmic phantom inferred from ancient scars. But what if a hidden star was not distant but buried deep within another? This brings us to a stellar paradox so strange it sounds like science fiction, a cosmic Russian nesting doll of unimaginable density. Imagine a red supergiant star, one of the largest and most bloated objects in the universe, its outer layers stretching hundreds of millions of miles. Now picture that at its very heart, where you would expect a seething nuclear furnace, there is instead a city-sized sphere of pure neutronium, the collapsed remnant of a dead star. This theoretical hybrid is known as a Thorne-Zitkow object, named for the physicists who first proposed its existence. From the outside, it would look almost indistinguishable from a normal red supergiant, glowing with a cool, ruddy light. You could point a telescope right at it and never suspect the secret ticking away in its core. The formation story is one of stellar cannibalism. In a close binary system, a massive star explodes as a supernova, leaving behind its incredibly dense neutron star core. If the explosion does not kick the two stars apart, the neutron star's orbit can decay, slowly spiraling inward through the outer layers of its giant companion. Over thousands of years, it plunges all the way to the center, becoming a new, bizarre engine. The physics inside such an object are unlike anything else in the cosmos. The intense heat and pressure from the neutron star's surface would trigger unusual nuclear fusion reactions in the surrounding gas, producing a distinct cocktail of heavy elements like rubidium, lithium, and molybdenum. This unique chemical signature is the only way astronomers could hope to identify one. For decades, the Thorne-Zitkow object remained a fascinating thought experiment. Then, in 2014, astronomers announced a candidate, a red supergiant in the Small Magellanic Cloud, known as HV 2112, showed an atmospheric composition overflowing with those telltale heavy elements. It was a thrilling hint, a star that perfectly matched the theoretical fingerprint, yet confirmation is extraordinarily difficult. The predicted signals are subtle, and other processes could potentially mimic them. The star remains a candidate, not a confirmed discovery. This makes the Thorne-Zitkow object a perfect example of a hidden star in plain sight. It represents a stellar identity crisis, a celestial body wearing the mask of a gentle giant while hiding the heart of a monstrous relic. Its very existence challenges our categories, asking us if a star is defined by its appearance or by the unimaginable reality burning silently within. The idea of a star hiding within a star stretches our understanding of cosmic identity. But what if the very first stars in the universe were born from a power source we cannot see at all? This leads us to one of the most profound theoretical concepts in cosmology, the dark star. These would not be stars as we know them today, powered by the fierce nuclear fusion of hydrogen into helium. Instead, dark stars are imagined as the universe's primordial giants, fueled by something far more mysterious, the annihilation of dark matter. In the dense, hot soup of the early cosmos, vast clouds of hydrogen and helium would have begun to collapse under their own gravity. According to the Standard Model, this gravitational energy heats the core until nuclear fusion ignites and a star is born. But theorists propose an alternative path. If those ancient clouds were also seeded with a high density of certain types of dark matter particles, a different process could take over. As the cloud condensed, dark matter particles trapped within it would collide and annihilate each other, releasing a tremendous, steady stream of heat. This dark matter furnace could counteract the gravitational collapse, preventing the core from ever getting hot enough for nuclear fusion to begin. The result would be a celestial object of staggering scale and paradox. A dark star could grow to be millions of times more massive than our Sun, and yet remain relatively cool and puffy, its energy radiating from a hidden, particle-based engine deep within. To our telescopes searching for the ultraviolet blaze of early fusion-powered stars, a dark star would be nearly invisible, a ghostly giant glowing with a faint, diffuse infrared warmth. Its light would not come from atoms, but from the silent destruction of the universe's most elusive substance. While no dark star has ever been observed, their potential existence solves several puzzling gaps in our understanding of the early universe. They could explain how supermassive black holes formed so quickly after the Big Bang, as these vast, unstable dark stars might have collapsed directly into the seeds of galactic monsters. They also offer a potential source for the faint, unexplained infrared glow that permeates the cosmos. The dark star represents the ultimate hidden star, one whose entire reason for shining is rooted in the invisible 85% of reality. It asks a fundamental question about cosmic dawn. Did the first lights in the universe come from fire we understand, or from a shadowy whisper of annihilation that we are still struggling to hear? Our vision of stellar death is a spectacular supernova or a fading ember, but the ultimate fate of most stars is a silence deeper than any we can conceive. After a star like our Sun exhausts its nuclear fuel, it sheds its outer layers, leaving behind a white-hot core called a white dwarf. This Earth-sized sphere of crystallized carbon and oxygen glows with residual heat, a fading memory of its former glory. For billions of years, it slowly cools, dimming from white to yellow to red and finally to infrared. But the cooling does not stop there. Given enough time, a timescale so vast it mocks human history, that last whisper of warmth would finally dissipate into the cosmic background. The white dwarf would become a black dwarf, a cold, dark sphere of pure crystal, adrift in the void. It would emit no light, no heat, no detectable radiation of its own. It would be a perfect stellar ghost, a fossil of a sun that once was, now invisible against the blackness of space. The staggering fact is that our universe is simply not old enough for even a single black dwarf to exist. The estimated time for a white dwarf to cool to this absolute zero state is many trillions of years, while our cosmos is a mere 13.8 billion years old. Every white dwarf we observe, no matter how dim, still retains a faint glow. So black dwarfs are hidden stars in the most profound temporal sense. They are the inevitable future of nearly every star you see in the night sky, a destiny written in physics but not yet realized in time. They represent the universe's final, quiet chapter, when all fusion has ceased and the last lights have gone out, leaving behind these dark, crystalline monuments to forgotten suns, drifting forever in an endless, starless night. Black dwarfs are a future written in the cold equations of time, but the darkness between stars is already home to a more immediate kind of ghost. Drifting through the interstellar void are countless solitary wanderers, worlds without suns. These are rogue planets, nomadic worlds violently ejected from their young solar systems in the gravitational chaos of planetary formation. To call them planets feels almost insufficient, for they are celestial orphans carrying the memory of a star they will never see again. They are, in a profound sense, hidden stars that failed to be. Many are likely gas giants, similar to Jupiter or Neptune, objects that began as stars due from a collapsing cloud of gas and dust, but simply never gathered enough mass to ignite the fusion furnace in their cores. They are the almost stars, the nearly wares, condemned to an eternal twilight. Detecting them is a monumental challenge. With no host star to illuminate them, they are cloaked in near-total darkness, visible only by the faint, residual warmth left over from their violent birth. This makes them virtually invisible to traditional telescopes searching for starlight. Astronomers have had to become cosmic detectives, employing a subtle trick of gravity known as microlensing. When one of these dark, massive worlds drifts almost perfectly in front of a distant background star, its gravity acts as a fleeting lens. For a few hours or days, it bends and magnifies the star's light, causing a temporary, characteristic brightening. It is a single, telltale flash in the data, a signature of an unseen mass passing silently through the foreground. Through this method, we have caught glimpses of a few of these lonely giants. One of the first confirmed rogue planets, known as OGLE 2012 BLG0724, is estimated to be a Jupiter-sized world untethered to any star roaming the galactic bulge. The implications are staggering. Some estimates suggest there could be billions, even trillions, of these nomads in our galaxy alone, outnumbering the stars themselves. They are the dark, silent majority of the cosmic population. Imagine the landscape of such a world, a perpetual night sky ablaze with the unmoving tapestry of the Milky Way, no sunrise ever coming, its surface frozen to temperatures near absolute zero, yet perhaps with a hidden, tidally heated ocean deep beneath an ice shell, a pocket of warmth in the eternal dark. These rogue planets redefine the concept of a solar system and expand the potential arenas for life into the most desolate, starless realms. They are the ultimate hidden celestial bodies, not by distance or disguise, but by their fundamental nature as shadows cast by no light. The dark wanderers drifting between stars are cosmic orphans, but our own solar system may harbor a hidden giant of its own. A phantom world whose presence is felt only through the subtle tremors it sends through the orbits of its neighbors. This is the compelling mystery of Planet 9, beyond the icy realm of Neptune. In the frozen, sunless expanse of the Kuiper belt, a strange pattern has emerged. A collection of small, distant objects, icy bodies like Sedna, share a peculiar orbital alignment. Their elongated paths around the Sun are clustered together, their points of closest approach tilted in the same direction, as if herded by an unseen gravitational hand. The odds of this happening by random chance are astronomically low. The most elegant explanation, proposed by astronomers Konstantin Batygin and Mike Brown in 2016, is a massive, undiscovered planet. This theoretical world would be a true giant, perhaps 5 to 10 times the mass of Earth, a super-Earth or a mini-Neptune lurking in the perpetual twilight. Its orbit would be staggering, a vast, elliptical loop so distant that a single trip around the Sun could take 10,000 to 20,000 years. At its farthest point, it would be over 20 times farther from the Sun than Neptune, a place where our star is just a particularly bright point in an otherwise black sky. This incredible distance is precisely why we have not seen it. A planet does not generate its own light, it only reflects the sunlight that falls upon it. Out there, sunlight is desperately feeble, a billion times dimmer than it is here on Earth. Any reflected light from this world would be an incredibly faint, slow-moving speck against a backdrop of millions of stars, a needle in a cosmic haystack that is also moving. The ongoing search for Planet 9 is a testament to patience and computational power. Teams are using some of the world's most powerful telescopes, like Subaru in Hawaii, to scan vast swaths of the predicted orbital path, taking images months apart and looking for that one tiny dot that has shifted its position. Its discovery would be a monumental event, rewriting the textbooks on our solar system's formation and architecture. It would be the first true new planet discovered orbiting our Sun in over 170 years and the largest found in that time. More than a trophy, its existence would solve the Kuiper belt's orbital puzzle and could explain other solar system mysteries like the unusual tilt of the Sun's axis. Planet 9 represents a different kind of hidden star, a world whose reality is written not in light but in the gravitational whispers of the distant ice. It is a ghost inferred from the disturbed paths of smaller ghosts, a king waiting in the dark to be crowned. Planet 9's potential presence is written in the gravitational disturbances of distant ice, but some stars hide their true nature within the very light they emit. There are beacons scattered across the cosmos, stars whose rhythmic pulses hold the key to the universe's grandest scale, yet they remain utterly invisible to the naked eye as anything more than a faint smudge. These are the Cepheid variable stars in other galaxies. In our own Milky Way, we can study these pulsating giants as individual points of light, watching them brighten and dim with a precise clockwork regularity. Their true power, however, lies in their role as cosmic yardsticks. A century ago, astronomer Henrietta Leavitt discovered a beautiful, fundamental relationship for Cepheids. The longer their pulsation period, the greater their true, intrinsic brightness. This means if you can measure how fast a Cepheid pulses, you know exactly how luminous it truly is. By comparing that known luminosity to how dim it appears from Earth, you can calculate its distance with remarkable accuracy. They became the first crucial rung on the cosmic distance ladder. But to measure the universe itself, we needed to find these stellar lighthouses in galaxies far beyond our own. Herein lies the challenge of their hidden nature. When you look at the Andromeda Galaxy, 2.5 million light-years away, what do you see with a small telescope? A fuzzy oval of diffuse light. That glow is the combined radiance of over 1 trillion individual stars. A Cepheid variable within it is just one star among that unimaginable multitude, its light completely blended with its neighbors. To the unaided eye and to most telescopes, it is utterly lost, hidden in plain sight within the galactic glow. Its vital pulse is invisible. The only way to tease it out is with the extraordinary resolving power of a telescope like Hubble, positioned above Earth's blurring atmosphere. Hubble can stare at a single patch of that fuzzy oval for hours over many nights and pick out individual points of light. Astronomers search for stars whose brightness changes over days or weeks. When they find one that pulses with the classic Cepheid rhythm, they have struck gold. By timing its pulse, they know its true wattage. By measuring its apparent faintness, they can calculate the distance to its host galaxy itself. This is how we measured the expansion rate of the universe and confirmed the existence of dark energy. Every major galaxy whose distance we know with confidence likely has its value anchored by the careful observation of these hidden, pulsating stars within it. They are luminous giants, yet they vanish into the crowd, their most important signal, their rhythmic beat, silenced by distance until we train our most powerful eyes upon them. They remind us that sometimes the most critical truths are not shouted but whispered, lost in a chorus of light until we learn how to listen. The Cepheid's rhythmic pulse fades into the galactic chorus, but our own galaxy's structure creates a more permanent form of cosmic silence. There is a place where the Milky Way itself blocks our view, a vast and impenetrable wall of light and shadow. This is the galactic bulge, the central, swollen hub of our spiral galaxy. From our vantage point in the Orion Arm, we gaze toward the center of the Milky Way in the constellation Sagittarius. What we see is not a clear window, but a spectacular, dense cloud of stars, gas, and dust. Hundreds of billions of stars are packed into this central region, their collective glow creating a soft, milky band across our sky. This is beautiful, but it is also a celestial barrier. The sheer density of material in the bulge acts like a colossal curtain, absorbing and scattering visible light. It creates a permanent blind spot, a cosmic zone of avoidance that completely obscures our view of anything that lies directly behind it. We cannot see through it with optical telescopes, any more than you could see a lighthouse through a raging blizzard. This means there is an entire half of the universe, a vast cone of space extending out from the far side of the galactic center that is forever hidden from our direct sight. What wonders are concealed there? Entire spiral galaxies, rich star clusters, glowing nebulae, all could be positioned in that direction, and we would have no optical clue of their existence. Astronomers know this region is not empty, of course. We can use other wavelengths like radio and infrared to peer through some of the dust, revealing hints of structure. But for visible light, the curtain remains drawn. It is a profound reminder of our limited perspective. We map the cosmos from a single point, and our own home galaxy physically prevents us from seeing a significant portion of it. Every star, every object in that hidden zone is a hidden star from our earthly point of view. They shine, they evolve, they live their cosmic lives in a realm of permanent optical twilight, forever separated from our gaze by the brilliant, crowded heart of our own Milky Way. This cosmic curtain is not merely a passive obstruction, it is an active frontier of discovery. Astronomers call it the zone of avoidance, a strip of sky accounting for nearly 20% of the celestial sphere where our view of the distant universe is completely wiped out. The problem is not darkness but overwhelming light and matter. The disk of our Milky Way is filled with billions of stars, vast clouds of obscuring dust and glowing nebulae. This material absorbs and scatters the visible light from anything behind it, like trying to see a distant mountain through a dense, brilliant fog. For centuries, this meant our maps of the cosmos had a glaring blank patch. We could chart galaxies in every other direction, building a three-dimensional model of the universe, but that zone remained a terra incognita, a fundamental blind spot in our cosmic cartography. What lay hidden there, entire galactic superclusters, the largest structures in the universe, could be lurking just out of sight, forever altering our understanding of the cosmos's large-scale architecture. The frustration sparked ingenuity. To see through the interference, astronomers had to abandon the eyes they were born with and learn to see in new ways. They turned to telescopes that detect radio waves and infrared light. These longer wavelengths can punch through the dusty veil that blocks visible light. Radio waves, in particular, slip between dust grains with ease, allowing instruments to map the hydrogen gas that permeates spiral galaxies. It is a form of cosmic echolocation. By tuning into the specific radio signature of hydrogen, teams have painstakingly scanned the zone of avoidance, revealing the ghostly outlines of hundreds of previously hidden galaxies. One dramatic discovery was the Dwinjaloo 1 galaxy, a large spiral found in 1994 hiding just 10 million light-years away, almost on our galactic doorstep yet completely obscured. In infrared, the view is different. Dust itself glows with warmth, but so do the stars shrouded by it. Space telescopes like Spitzer and WISE have mapped the heat signature of the zone, piercing the gloom to reveal the dense star-forming regions and stellar nurseries buried within our own galaxy's bulge, while also spotting the telltale infrared glow of distant, hidden galaxies behind it. Each new detection is like finding a continent on a medieval map. These efforts remind us that our view of the universe is profoundly shaped by our location within it. We are not passive observers on a clear stage. We are peering out from within the crowded balcony, standing on tiptoe and using every tool at our disposal to glimpse the hidden performance unfolding just behind the glare of the spotlight. Piercing the galactic curtain reveals distant lights, but to find the universe's very first stars, we must journey back in time to an era before curtains, before galaxies, before anything but the purest elements. These are the population 3 stars, the primordial giants whose birth ignited the cosmos. Theory tells us they formed from clouds containing only hydrogen and helium, the pristine elements forged in the Big Bang's first moments. Without heavier atoms to help radiate heat away, these clouds could collapse into monsters, stars hundreds of times more massive than our Sun. They would have burned ferociously bright and died young in cataclysmic supernova, seeding the universe with the first heavy elements, the carbon, oxygen, and iron that make up our world and our bodies. Yet for all their importance, they remain the ultimate hidden stars, ghosts of the cosmic dawn. Why can we not see them? The answer lies in an overwhelming combination of distance and time. The light from these first stars has been traveling for over 13 billion years. The expansion of the universe has stretched that ancient light into the far infrared, a wavelength our eyes cannot see, and that is difficult to detect from Earth. Furthermore, they are incredibly faint points lost in the haze of the earliest galaxies. Our most powerful telescopes, like the James Webb Space Telescope, are designed to peer into this epoch, but they likely cannot resolve a single, individual population 3-star. It would be like trying to pick out a single candle flame from across a vast, foggy valley at dusk. So astronomers must become cosmic chemists, searching not for the stars themselves, but for their unique signature. They turn their instruments toward quasars, the brilliant cores of ancient galaxies powered by supermassive black holes. These quasars act as cosmic lighthouses. Their intense light shines through the primordial gas clouds that existed between them and us. When that light finally reaches our telescopes, it carries an absorption fingerprint. Specific wavelengths are missing, absorbed by the atoms in those intervening clouds. By analyzing these dark lines in the quasar's spectrum, scientists can deduce the chemical composition of the early universe. The Holy Grail is finding a cloud that shows only hydrogen and helium with no traces of heavier elements. Such a pristine cloud would indicate it has never been polluted by the supernova debris of earlier stars. It would mark a pocket of the universe still waiting for its first star to be born, or one that has just witnessed that first pure explosion. Finding this chemical fingerprint is the closest we may ever come to touching the dawn of light. These hidden first stars are more than just historical curiosities. They are our cosmic ancestors. Their short, violent lives forged the very elements that would eventually coalesce into rocky planets, oceans, and life. We are literally made from the ashes of stars we have never seen, the silent, invisible giants whose first light ended the universe's dark ages and began the story of everything we know. The ashes of the first stars seeded the cosmos with the dust that would one day hide their descendants. Within the spiral arms of galaxies like our own, this dust gathers into immense cold clouds, cosmic wombs so dense they swallow light whole. These are dark nebulae, and inside their inky depths, new stars are being born in total secrecy. One of the most famous is Barnard 68, a small, opaque blob in the constellation Ophiuchus. Through an optical telescope, it appears as a perfect hole punched in the starfield, a circle of nothingness. But that darkness is not empty. It is a thick shroud of gas and dust, a stellar nursery in its earliest, quietest phase. Gravity is slowly pulling the cloud inward, heating a core that will one day ignite. For now, the infant star or stars forming at its heart are completely hidden, insulated from the outside universe by a blanket 1 trillion miles thick. They are invisible not by distance or exotic physics, but by being swaddled in the very material that created them. This hidden state is temporary but crucial. The cocoon protects the fragile, accreting star from disruptive radiation and allows it to gather mass in peace. Eventually, the star's nuclear furnace will roar to life. Its first act will be one of violent revelation. Intense radiation and powerful stellar winds will stream outward, pushing against the surrounding cloud, slowly eroding it from the inside out. Imagine a light being switched on in a dense fog, the glow diffused at first, then gradually carving out a cavity of clarity. We see this dramatic process frozen in time across the galaxy. The iconic pillars of creation within the Eagle Nebula are a breathtaking example. Those towering, elephant trunk columns of dust are not solid structures but evaporating gas. At their tips, hidden from our direct view, newborn stars are firing intense ultraviolet radiation, photo-evaporating the very pillars that birthed them, sculpting them into their haunting forms. The famous Horsehead Nebula is another silhouette of concealment, a dark knot of dust projected against a glowing background. its shape defined by the hidden young stars behind it whose light it blocks. These nebulae are cosmic curtains, and the stars within are actors waiting in the wings, their eventual emergence a spectacular, destructive part of their birth. To witness a dark nebula is to see the universe's patience, a promise of light written in the deepest dark. Mera, the Wonderful, lives up to its name. In the constellation Cetus, this ancient star performs a slow, mesmerizing dance of light and shadow visible across the centuries. For most of its 332-day cycle, Mera shines brightly enough to be seen with the naked eye, a steady beacon. Then it begins to fade. Over weeks and months, its light dwindles, its fire seeming to gutter out until it vanishes completely from our unaided view. For roughly 5 months of every year, Mera is a hidden star, lost in the stellar background, only detectable through the eye of a telescope. Then, with the same slow patience, it rekindles itself, swelling and brightening back to its full glory. This makes Mera the prototype for an entire class of hidden stars, the long-period variables. They are not obscured by dust or distance, but by their own rhythmic nature, periodically dimming below the threshold of human vision. Their hiding is a scheduled performance, a cosmic pulse written in light. The discovery of Mera's variability in 1596 by the astronomer David Fabricius marked a pivotal crack in the ancient celestial dogma. For millennia, the fixed stars were considered perfect and unchanging, a permanent backdrop to the wandering planets. Mera proved that stars could change, could live and breathe in cycles grander than a human lifetime. It was the first observational evidence that the heavens were not static but dynamic, opening the door to modern astrophysics. Today, we understand Mera variables as aging red giants in a late, unstable stage of life. Their outer atmospheres have expanded to titanic proportions, becoming so tenuous that they pulse in and out like a vast, slow heartbeat. As the star contracts, it heats and brightens. As it expands, it cools and dims. This regular oscillation makes them celestial lighthouses with a fading beam, visible and then hidden on a schedule older than recorded history. They remind us that the cosmos is alive with change, and that sometimes the most wonderful things are those that know when to disappear. Mera's gentle pulse is a scheduled disappearance, but some stars hide in a far more permanent and crowded twilight. Venture into the heart of a globular cluster, a spherical swarm of hundreds of thousands of ancient stars bound together by gravity. From a distance, it looks like a fuzzy, celestial dandelion head. But as you travel inward, the density of stars increases exponentially. In the very core, the stellar population becomes so unimaginably packed that even our most powerful telescopes, like Hubble, reach their limit. The light from countless stars blends into a single, brilliant, and unresolved glow. It is a stellar traffic jam of epic proportions, where stars are separated by mere light weeks instead of light years. Within that seething core, a fascinating cosmic sorting has occurred, a process called mass segregation. Over billions of years, through countless gravitational interactions, the heavier stars, the bright giants and the dense stellar remnants like neutron stars, slowly sink toward the cluster's center. The lighter stars, the countless faint red dwarfs and cooling white dwarfs, are gently nudged outward or remain lost in the background. The result is a core dominated by brilliant, massive stars whose combined glare acts like a celestial spotlight, blinding us to the fainter multitude. Imagine standing in a packed stadium at night, where everyone in the front rows is holding a powerful flashlight pointed at your eyes. Behind that wall of blinding light, you know there are thousands more people, but you cannot make out a single face. That is the core of a globular cluster. Hidden within that unresolved glare are likely thousands of red dwarfs, the most common stars in the universe, each burning feebly for trillions of years. Mixed among them are the ghostly white dwarfs, the faded cores of dead stars, emitting only a faint whisper of leftover heat. These stars are not invisible because they are dim, they are invisible because they are drowned out. Their light reaches our telescopes, but it is mathematically inseparable from the overwhelming brilliance of their luminous neighbors. To find them, astronomers must use statistical tricks and subtle color analyses, inferring their presence from the overall properties of the light rather than seeing them directly. These hidden cores represent a stellar census we cannot complete, a reminder that sometimes the most common things in the universe are the hardest to see, lost not in darkness but in a crowd of light. The overwhelming glow of a globular cluster hides stars through sheer brilliance, but the greatest veil of all is woven from the fabric of space and time itself. To find a star so far away its light is a whisper from the dawn of creation requires a perfect cosmic alignment, a celestial miracle. That miracle has a name, Earendel. In March of 2022, astronomers using the Hubble Space Telescope announced they had detected the light of a single star from a time when the universe was only 7% of its current age. Its light has been traveling toward us for 12.9 billion years. This is not a galaxy, a blur of billions of stars, but a solitary sun, now magnified and revealed by a phenomenon of breathtaking precision. Earendel exists in a region of space so remote it should be forever, absolutely hidden. At that distance, even the most luminous stars are vanishingly faint points, their light stretched and dimmed by the relentless expansion of the cosmos. Seeing it directly would be like trying to spot a single firefly on the moon with the naked eye from Earth. It was only made possible by a natural telescope of immense power, a gravitational lens. Between us and Earendel lies a massive cluster of galaxies known as WHL 0137+08. The combined gravity of this cluster warps the space around it, creating a lens that bends and magnifies the light from objects far behind it. Think of it as a natural magnifying glass floating in space, but one that also creates multiple distorted images. In a stroke of extraordinary luck, Earendel was positioned almost perfectly along a ripple in this lens, a region of extreme magnification called a caustic. This alignment boosted its brightness by a factor of thousands for a fleeting moment in cosmic time, allowing Hubble to pick out its pinprick of light. The star's very name, from Old English meaning morning star or rising light, reflects its place at the cosmic dawn. What we see is not the star as it is today. A star with that mass would have lived only a few million years before exploding in a supernova. Earendel died eons ago. We are witnessing a single, fossilized snapshot of its life, a beam of light that began its journey when the universe was in its infancy. Its discovery pushes the boundary of what we thought possible to observe, proving that with the right cosmic alignment, even the most distant, hidden individuals can step into the light, if only for a moment. Earendel's ancient light is a fossilized whisper from the dawn, but some stars are screaming to be heard right now from the very edge of oblivion. Within the hearts of the most violent galaxies, a different kind of hidden star endures a perpetual apocalypse. These are the stars that dare to orbit an active galactic nucleus. An active galaxy is one whose central supermassive black hole is not dormant, like our own Sagittarius A star, but is actively feeding. Vast rivers of gas, dust, and shredded stars spiral inward, forming a seething, superheated structure called an accretion disk. This disk is a maelstrom of plasma, glowing with the heat of millions of degrees and blasting out enough X-rays and gamma rays to sterilize entire solar systems. It is the most hostile environment imaginable, yet theory and some tantalizing observations suggest that stars can survive here, not in serene orbits, but in frantic, doomed paths within or just above this cosmic hurricane. Their existence is a testament to gravity's relentless grip. How could a star form in such chaos? One possibility is that dense clumps within the accretion disk itself could collapse directly under their own gravity, sparking fusion in a baptism of fire. Another is that entire star clusters wandering too close to the galactic center could be torn apart with a few hardy stars captured into tight, screaming orbits around the monster. These stars would live a life of extremes, bathed in lethal radiation, bombarded by high-energy particles, and scoured by supersonic winds of gas. Their surfaces would be constantly ablated, stripped away atom by atom. They might appear not as serene points of light, but as cometary blurs, trailing tails of their own vaporized material. And here lies the reason they are hidden stars. The very medium that defines their existence also conceals them. The accretion disk is dazzlingly bright, outshining the combined light of every star in its host galaxy. The glare from this tiny central engine is so intense that it drowns out the light of any individual star orbiting within it. It is like trying to spot a single sparkler being waved in front of the blinding beam of a lighthouse searchlight. Furthermore, the disk is not transparent. It is a thick, turbulent fog of plasma. Any star orbiting within it would be perpetually shrouded, its light absorbed and scattered before it could ever escape to reach our telescopes. We infer their possible existence from subtle, rapid flickers in the brightness of some active galactic nuclei, fluctuations that could be explained by stars or dense gas clouds crossing the face of the brilliant disk. To live on such a world, if it could even hold onto planets, would be to know no night. The sky would be a perpetual, blinding white, etched with swirling arcs of incandescent gas, the central black hole's shadow perhaps visible as a dark vortex in a storm of light. These stars are hidden not by distance or dust, but by the sheer, overwhelming fury of their own neighborhood. They are prisoners of light, dancing in a cage of radiation from which their own faint glow can never escape. The fury of an active galactic nucleus represents one extreme, but the space between true stars and planets holds a quieter, colder secret. Brown dwarfs are the universe's failed stars, celestial objects caught in a perpetual identity crisis. They form just like stars from the gravitational collapse of a cloud of gas and dust, but they never gather enough mass to cross a critical threshold. In the core of a true star, the pressure and temperature become so immense that hydrogen atoms slam together, fusing into helium and releasing the torrent of energy that makes a sun shine. A brown dwarf falls short. With a mass between about 13 and 80 times that of Jupiter, its core gets hot, but never hot enough to ignite that sustained hydrogen fusion furnace. It is a star that never truly turned on. Instead, it glows with a dull, residual warmth from its violent birth, radiating almost entirely in the infrared spectrum, a heat signature invisible to our eyes. This makes them incredibly difficult to find. They are not bright beacons, but faint, cooling embers drifting in the dark. For decades, they were purely theoretical, hidden stars by their very nature. Then, in the 1990s, improvements in infrared detectors finally allowed astronomers to spot these dim ghosts. The discovery revealed a hidden population littering our galactic neighborhood. Current estimates suggest there could be as many brown dwarfs in the Milky Way as there are normal stars, meaning billions of these failed suns might be lurking unseen, many within just a few dozen light-years of our solar system. They are the silent majority of star-like objects, a shadow population we are only beginning to census. The coldest and most elusive class of these objects are the white dwarfs. These are the ancient, nearly dead embers of the brown dwarf family. Having cooled over billions of years, some have surface temperatures comparable to a warm summer day on Earth or even lower. They emit virtually no visible light, their warmth so faint it blends into the cold background of space itself. The first white dwarf confirmed, WISE 0855-0714, is a chilling example. Located just over 7 light-years away, making it one of the Sun's closest neighbors, it has a temperature of about -55 degrees Fahrenheit. You could theoretically hold your hand near it and feel almost nothing. From a cosmic perspective, it is essentially invisible, a frozen ghost world drifting in the void, detectable only by the most sensitive infrared telescopes as the faintest whisper of residual heat. A planet orbiting such a body would know no sunrise, only a permanent, deep twilight illuminated by the dull infrared glow of its failed sun, a sky devoid of the blue light that fuels life as we know it. Brown dwarfs complete a hidden spectrum of celestial objects, from the almost stars that never ignited to the cold, fading cinders that remind us how much of the cosmos exists in a state of quiet, infrared twilight. The cold twilight of a brown dwarf feels like a tangible frontier, but the true edges of reality may lie beyond our perception entirely. To find the next hidden star, we must leave the familiar three dimensions of space behind and step into the realm of pure theory. String theory, a leading candidate for a unified description of all forces, suggests our universe may have more than the three spatial dimensions we experience. It proposes tiny, curled-up dimensions at every point in space, scales so small they are forever beyond our direct reach. Within this framework, a staggering possibility emerges. Could entire stars or the collapsed remnants of stars exist in these hidden dimensions? These would be objects of a fundamentally different nature, bound by physics we can barely model, shining with light or other energies that have no pathway into our dimensional reality. To us, they would be utterly, perfectly invisible, not cloaked in dust, not dimmed by distance, but separated by the very architecture of spacetime itself. Yet, if they exist, they might not be completely silent. Gravity, according to Einstein's theory, is the curvature of spacetime. If these hidden dimensional stars have mass, they would warp the fabric of reality in ways that could, in principle, leak into our three-dimensional slice of the cosmos. Their presence might be felt only as a subtle, unexplained gravitational tug on the matter we can see. Imagine a universe where every galaxy we observe is accompanied by an invisible, dimensional twin, a shadowy stellar population whose gravity helps bind the visible stars together, yet whose light is forever trapped in a higher dimensional space. We would detect its influence as extra mass, a gravitational signature with no luminous source to explain it. This is, of course, deeply speculative. But it offers a tantalizing, radical solution to one of cosmology's greatest mysteries, dark matter. What if the missing mass that holds galaxies together isn't made of unknown particles in our dimensions, but of ordinary matter, even familiar stars, simply residing in a parallel spatial realm adjacent to our own? Their gravity would affect us, but their light would not. They would be the ultimate hidden stars, not by cosmic coincidence, but by the fundamental laws of existence. While this idea rests on the unproven foundations of string theory, it expands the very meaning of star into the geometric shadows of reality, suggesting the cosmos we see may just be the visible fraction of a far richer, multidimensional tapestry. Our cosmic journey now takes a sharp turn toward the intimate and the predatory, where stellar partnerships become scenes of quiet theft. In the silent expanse, two stars can become locked in a gravitational embrace so close that their fates are violently intertwined. This is the realm of the mass transfer binary, often called a vampire star system. Here, one star, typically a dense, compact white dwarf or neutron star, uses its immense gravity to literally suck the life out of its larger, bloated companion. The process begins with proximity. As the donor star ages and expands into a red giant, it can swell until its outer atmosphere spills over a gravitational boundary known as the Roche lobe. Past this point, the material no longer belongs to the star it came from, but falls under the dominant gravitational pull of its hungry neighbor. The siphoned gas does not fall directly onto the vampire star, however. Conservation of angular momentum causes it to spiral inward, forming a whirling, flat disk of superheated plasma called an accretion disk. This disk can shine brilliantly in X-rays, often becoming the most visible part of the system from great distances, while the stars themselves remain partially or fully hidden within its glare. In the most extreme cases, the donor star can become completely engulfed. The two stellar cores orbit inside a shared shroud of gas, a common envelope that hides them from view as they spiral closer together in a final, fatal dance. This vampiric act fundamentally rewrites the life story of both stars. The thief gains mass, which can trigger spectacular events. A white dwarf accumulating too much matter may cross a critical threshold and explode as a Type Ia supernova, a brilliant standard candle used to measure the universe. A neutron star gorging on stolen material can suddenly brighten as an X-ray burster, a flash of incredible energy, but the donor star suffers a stranger fate. Having its outer hydrogen-rich layers stripped away, it is left exposed as a hot, helium-rich core. This makes it appear younger, hotter, and bluer than it truly is, a stellar zombie masquerading as a youthful star. Its true age and evolutionary path are hidden beneath the scars of cosmic robbery. These systems are a reminder that in the cosmos, even light can be born from a kind of darkness, from one star hiding in the shadow, or within the stolen substance of another. The sun's brilliant face creates more than just daylight. It carves a permanent blind spot in the celestial map. Every single day, as our planet travels its annual path, there exists a cone of space directly opposite our position from the sun, a region forever washed out by solar glare. The stars residing there are, for that moment, completely and utterly hidden from us. This is not a matter of distance or exotic physics, but simple geometry and overwhelming light. Our most powerful telescopes are powerless against it, as pointing any sensitive instrument near the sun would risk catastrophic damage from its intense radiation. So, for roughly half the year, every star, galaxy, and nebula positioned in that specific zone of the sky is rendered invisible, lost behind the very heart of our own solar system. This hidden region is not static, it gracefully shifts with Earth's orbit. The stars eclipsed by the sun in January slowly emerge into the pre-dawn sky by July, as our changing vantage point around the sun brings them into view. This annual cycle meant that for centuries, a specific patch of stars remained a particular mystery. In the early 1800s, astronomers realized this solar blind spot held the key to measuring the universe. They needed to observe a star's parallax, the tiny apparent shift in its position against more distant background stars when viewed from opposite sides of Earth's orbit. To see this shift, you must observe the same star 6 months apart. But what if the perfect candidate star lay in that solar zone? For half the year, just when you needed the second measurement, it would be hidden behind the sun. This forced a patient, year-long wait for the Earth to circle around and bring the star back into the night sky. The star that finally cracked the cosmic distance scale, 61 Cygni, was chosen partly because its rapid motion suggested it was nearby, but also because its position allowed for clear observations spaced 6 months apart. The stars hidden behind the sun taught astronomers a lesson in celestial patience, proving that sometimes the greatest discoveries require waiting for our own world to move aside and reveal the universe's hidden landmarks. Our solar system's glare is a temporary curtain, but our galaxy is pulling a permanent river of stars from the sky. High above and below the plane of the Milky Way, a faint, arching ribbon of hydrogen gas stretches across 180 degrees of the southern sky. This is the Magellanic Stream, a colossal filament of matter torn from our two largest satellite galaxies, the Large and Small Magellanic Clouds. For decades, it was known only as a river of cold, diffuse gas, a ghostly scar from a close gravitational encounter with our galaxy hundreds of millions of years ago. Yet, where there is gas in such vast quantities, there must also be stars. The physics of galactic collisions dictates that when tidal forces rip gas clouds away, they also pull along any stars that were forming within them. This means the Magellanic Stream should be a stellar river too, a sparse trail of isolated suns and faint, loose star clusters that were kidnapped from their home galaxies and are now falling silently into the Milky Way. Finding them, however, is a monumental challenge. These stars are not clustered in a bright, obvious group. They are lonely wanderers scattered along a filament hundreds of thousands of light-years long, drifting through the vast, empty halo of our galaxy. Their light is incredibly faint, and they are projected against the dense, brilliant backdrop of the Milky Way's own starfields. Picking out a single, sun-like star that belongs to the stream from among the billions of foreground Milky Way stars is like trying to identify one specific grain of sand on a sunlit beach. It requires not just powerful telescopes but sophisticated stellar forensics. Astronomers must measure the precise motion, distance, and chemical composition of millions of stars to find the rare few whose trajectories and elemental signatures match an origin in the Magellanic Clouds. It is a slow, patient search for needles in a cosmic haystack that is itself in motion. The first confirmed stellar members of the stream were only identified in the last decade, a handful of distant, red giant stars whose motions betrayed their extragalactic origin. This discovery confirmed that the stream is not just a gas cloud, but a true stellar migration, a hidden population being silently assimilated. These stars are celestial refugees on an epic journey. Born in the dwarf galaxies next door, they were uprooted by our Milky Way's gravity and set on a billion-year fall into the galactic disk. Their eventual fate is to merge with the vast stellar population of our spiral arms, their unique heritage dissolved. To stand on a planet orbiting one of these hidden stream stars would offer a terrifying and majestic vista. The Milky Way would not be a band beneath your feet, but a colossal, looming wall of light dominating half the sky, its gravitational pull an inevitable tide drawing your world inward. Your own native galaxy, the Magellanic Cloud you once called home, would be a receding, fuzzy smudge in the distance, a memory fading with every passing eon. These stars represent a hidden dimension of galactic evolution, the silent, ongoing process of cosmic cannibalism written in faint starlight, a river of suns flowing into the great galactic sea. This river of stolen stars flows into a galactic sea, but a single sun can create its own cosmic storm, a final, furious performance before the curtain falls. Hidden Star 22 exists in a fleeting moment of stellar chaos, a phase so brief most stars pass through it in the blink of a cosmic eye. After a star like our Sun exhausts the helium in its core, it swells into a luminous but unstable giant on the asymptotic giant branch, or a GB. Here it pulsates violently, shedding its outer layers into space in a series of mighty stellar winds. But what happens next is not an instant transition. The star leaves the GB stage, its nuclear fires beginning to shut down for the last time. It starts to contract and heat up rapidly, yet it is still surrounded by the vast, expanding cloud of its own discarded material. For a mere few thousand years, a celestial blink, the star is caught in this transitional state. Astronomers call it a post-GB star, and its visible manifestation is a protoplanetary nebula. The name is a bit of a misnomer. It has nothing to do with planet formation. It is called protoplanetary because through small telescopes of centuries past, these objects looked like the fuzzy, greenish disks of newly forming planetary systems. In reality, it is a star hiding in plain sight, shrouded by its own funeral shroud. The physics at play are exquisite and violent. The central star, now a hot, dense core, begins blasting out a fast, thin stellar wind. This newer wind slams into the slower, thicker cloud of dust and gas ejected during its earlier GB phase. The collision is catastrophic and sculptural. It does not create a smooth sphere. Instead, the star's rotation and magnetic fields often funnel the fast wind into two opposing jets, punching through the dense cloud like twin blowtorches. This carves out intricate bipolar structures, vast hourglasses or butterfly wings of glowing gas millions of miles across, and here is where the hiding occurs. The central star is blazing hot, but it is also very small, perhaps only the size of Earth. its visible light is overwhelmingly outshone by the surrounding nebula it has illuminated. Worse, the dense regions of the dust cloud itself do not merely glow, they scatter and reflect the star's light. In many cases, the star is positioned within a thick, dusty torus, a donut-shaped ring encircling its waist. From our vantage point, that dusty ring can block our direct view of the star completely. We see the magnificent, illuminated lobes of the nebula, but the brilliant engine at its heart is obscured, its light diffused and redirected by the very debris it expelled. The iconic Egg Nebula, or CRL 2688, is a perfect example. Hubble images reveal breathtaking searchlight beams and concentric rings of dust, a celestial sculpture of shadow and light. Yet the central star is invisible, hidden within the dark band of dust that girdles the nebula's center. We know it is there because its intense ultraviolet radiation causes the gas to fluoresce, and its infrared heat signature glows through the dust. But to optical telescopes, it remains a ghost in its own mansion. This phase is the star's final, frantic attempt to reveal itself, a last burst of artistic creation that ironically conceals the creator. It is a beautiful paradox, a cosmic masterpiece signed with a hidden name. The magnificent sculpted nebula is a final signature, but the galaxy's true autobiography is written in a far more ancient and diffuse script. High above and below the brilliant spiral arms of the Milky Way, in a vast and nearly empty spherical volume, drifts a sparse population of ancient suns. This is the galactic halo, and the stars within it are the galaxy's oldest living fossils. Unlike the crowded, bustling disk where our sun resides, the halo is a desolate frontier. Its stars are not concentrated in a flat plane but scattered in all directions, orbiting the galactic center on long, slow, and often inclined paths. They are the surviving pioneers from the Milky Way's violent infancy over 13 billion years ago. Their isolation and incredible age make them profoundly important, yet they are also deeply hidden. Why are these halo stars so difficult to see? The answer is a combination of distance, faintness, and sheer emptiness. Imagine you are in a vast, dark field at night. In one direction, you see a bustling, well-lit city. That is the galactic disk, packed with bright, young stars and glowing nebulae. Now look straight up into the black sky above you. Here and there, you might spot a single, distant porch light, miles away from any other. Those isolated, faint points are the halo stars. They are often incredibly old, population 2 stars, which means they formed from gas that contained almost no heavy elements. This lack of metals makes them inherently fainter and redder than younger stars like our Sun. Furthermore, they are spread across an immense volume of space. A typical halo star might be tens of thousands of light years above the galactic plane, adrift in the cold void. From our position within the disk, spotting one of these ancient suns is an extraordinary challenge. Its faint light must travel that vast distance and then pierce through the crowded foreground of billions of closer, brighter disk stars that lie in the same line of sight. It is like trying to pick out a single, dim candle flame on a distant mountain peak while standing in the middle of Times Square at night. For centuries, these stars were almost invisible to us, their light lost in the stellar glare. Their discovery required a new kind of astronomical detective work, focusing not just on brightness but on motion and chemistry. Astronomers learned to identify them by their high velocities. Halo stars orbit in a different direction and at different speeds compared to the orderly rotation of the disk stars. By measuring the radical, plunging paths of these runaway stars, we could trace them back to the halo. Their chemical fingerprint is even more telling. When analyzed with a spectroscope, their light reveals an atmosphere almost pure in hydrogen and helium, with only the faintest traces of elements like iron or carbon. This pristine composition marks them as relics from a time before the galaxy was enriched by generations of supernova. Each one is a time capsule from the cosmic dawn. To stand on a planet orbiting such a star would be to experience the ultimate isolation. The night sky would be shockingly, profoundly black. The magnificent spiral arms of the Milky Way would stretch below you like a distant, glowing bridge, a brilliant metropolis you could see but never reach. Your own sun, a dull red ember, would provide little warmth, and its light would have shone for so long that it predates the Earth itself. These hidden halo stars are the galaxy's foundation stones, the quiet elders whose silent orbits hold the memory of how everything began. The brightest beacon in our night sky holds a secret in its shimmer. Sirius, the dog star, blazes with a piercing white light, a constant in human skies for millennia. Yet its brilliant glare concealed a companion so perfectly it took nearly a century of stubborn deduction to prove it was there. In the 1840s, the German astronomer Friedrich Bessel noticed something peculiar. Sirius was not moving in a straight line across the heavens. Instead, it traced a gentle, wobbling path, as if an unseen partner were tugging it back and forth in a slow, gravitational dance. Bessel proposed the existence of a dark companion, a hidden star whose mass caused this telltale wobble. The prediction was bold, but the proof was elusive. For decades, astronomers trained their telescopes on Sirius, searching for any hint of this phantom in the overwhelming glare of the primary star. It was like trying to spot a speck of dust clinging to the lens of a brilliant searchlight. The challenge was not just brightness but contrast. The hidden companion we now know is Sirius B, a white dwarf. It is the incredibly dense, Earth-sized core of a once normal star that has exhausted its fuel and collapsed. Though ferociously hot, its surface area is minuscule, so it emits only a tiny fraction of the visible light of its gigantic partner, Sirius A. In 1862, American telescope maker Alvan Clark finally achieved the impossible. While testing a new, high-quality lens, he pointed it at Sirius and, in a moment of perfect atmospheric stillness, saw a faint, steadfast pinprick of light nestled right beside the dazzling star. The dark companion was not dark at all, but merely drowned out. The visual discovery was a triumph of prediction over perception. The story of Sirius B reveals a fundamental truth about our cosmic neighborhood. The stars we see as solitary points are often entire systems, and the most obvious brilliance can be the perfect cloak for a hidden reality. To understand Sirius B is to grasp a stellar afterlife. It is a sun that has died, its outer layers blown away, leaving behind a core of degenerate matter so dense that a single teaspoonful would weigh many tons on Earth. It orbits its vibrant partner every 50 years, a silent, dense ghost circling a brilliant giant, a hidden chapter in the biography of the night's most famous star. Sirius B is a ghost hidden by its partner's light, but entire galaxies can perform a far grander act of cosmic concealment. Some of the rarest structures in the universe are polar ring galaxies. Picture a classic spiral galaxy, a flat, spinning disk of billions of stars, like a glowing celestial plate. Now imagine a second, separate ring of stars, gas and dust, an entire cosmic halo, caught in a gravitational embrace and set into orbit. But this ring does not align with the plate. It spins at a right angle, orbiting over the galaxy's poles, perpendicular to the main disk. It is as if someone took a giant, star-studded hula hoop and threaded it around a spinning plate, creating a stunning celestial gyroscope. The origin of these rings is a mystery of galactic violence. They are likely the remnants of a dramatic theft. Billions of years ago, a smaller galaxy ventured too close to the larger spiral. Instead of a full merger, the spiral's immense gravity delicately stripped the passerby apart, capturing its stars and gas and weaving them into this extraordinary perpendicular ring. The captured stars within that ring now live a hidden life. From our perspective here on Earth, geometry is everything. If we view a polar ring galaxy perfectly edge-on, the spectacle is clear. We see the thin line of the main disk crossed by the bright band of the ring, a celestial plus sign etched in starlight, but the universe rarely offers us perfect angles. More often, we see these galaxies tilted, and from many of these oblique viewpoints, the ring stars become prisoners of perspective. The bright, dense core of the main galaxy, blazing with the combined light of millions of stars, can lie directly in front of sections of the ring, blotting them out. Thick lanes of dust swirling within the main disk further obscure the ring's light, acting like a cosmic veil. The stars in the ring are not intrinsically dim. They are simply hidden behind the brilliant foreground of their own host galaxy. Studying them is an exercise in peeling back layers of light. Astronomers must use filters to isolate specific wavelengths or rely on the subtle tug of the ring's gravity on visible stars to map its full, hidden extent. These stars orbit in a profound isolation, tracing a path that defies the galaxy's primary plane, a captured population forever circling in a perpendicular sky. To stand on a world within such a ring would be to experience a galaxy turned on its side. The majestic spiral arms of the main disk would not stretch across your heavens as a band, but would rise like a luminous, vertical wall, a waterfall of stars cascading from the zenith to the nadir. You would live in a stellar stream divorced from the galaxy's primary rhythm, a citizen of a stolen kingdom forever orbiting at a right angle to everything else. Dark matter's shadowy influence might not only power stars but birth them in the cold void. This concept pushes the idea of dark stars a step further into the very ignition of stellar life. We have seen how theoretical dark stars could be sustained by dark matter annihilation. But what if that same process, the silent collision of invisible particles, could act as the initial spark? In the standard model of star formation, a cloud of gas must collapse under its own gravity, heating up until nuclear fusion ignites. That heat comes from the gravitational energy of the collapse itself. But in the vast, frigid halos of dark matter that surround galaxies, there exist pockets of hydrogen gas that are simply too diffuse, too cold, and too isolated to begin that collapse on their own. They linger in a state of perpetual quiet, potential stars that never get started. Now introduce a dense knot of a specific type of dark matter into the heart of such a cloud. As these particles annihilate, they release a steady, gentle drizzle of energy directly into the surrounding gas. This is not a roaring furnace, but a cosmic space heater. This subtle, pervasive warmth could be enough to tip the balance. By providing an external source of heat, the dark matter prevents the gas from radiating away what little energy it has, allowing pressure to build and gravity to finally gain the upper hand. The cloud begins to condense around this dark, warm core. The resulting star would be a hybrid from its very first breath. Its initial contraction, the very act of its birth, would be aided not by gravity alone, but by the silent fire of annihilation happening in its heart. These stars would be hidden in a dual sense. First, they would likely form in the isolated outskirts of galaxies, within those massive, invisible dark matter halos where few conventional stars ever venture. They would be lonely lights in a profoundly dark neighborhood. Second, their formation mechanism is so alien, so removed from the processes we see in our own galactic backyard, that we might not even recognize them as stars at first glance. Their light and heat signature could be unusual, bearing the chemical imprint of having formed under this strange, shadowy influence. They would be cosmic foundlings raised by an invisible force. Finding such a star would be a direct glimpse into the handshake between the visible and invisible universe, proof that dark matter does not just shape galaxies gravitationally, but can actively participate in the creation of their light. It suggests that the darkness is not merely an empty stage, but a generative void capable of kindling fire in the cold. The brilliant, volatile shoulder of Orion holds a secret within its crimson glow. Betelgeuse, the titanic red supergiant destined to explode, may not be dancing alone. For years, astronomers have pieced together subtle clues suggesting this ancient star has a hidden partner, a companion star swallowed by its grandeur. The evidence is not a direct image, but a collection of whispers in the data. First, there is the star's motion. Betelgeuse does not travel through space in a perfectly straight line. It exhibits a slight wobbling drift. This kind of motion is often the gravitational signature of an unseen companion, a silent tug on the giant as it moves. Second, and more intriguing, are the strange asymmetries observed in its vast, puffy atmosphere. When viewed with sophisticated interferometers, Betelgeuse does not appear as a smooth, round disk. Instead, it shows colossal, shifting plumes of hot gas and immense cold spots, a dynamic and lopsided chaos. Some theorists propose these irregularities could be stirred, or even caused, by the gravitational influence of a second star orbiting within the supergiant's outermost layers. Imagine a planet-sized object, or even a small star, plowing through the tenuous outer atmosphere of a cosmic behemoth. Its gravity would churn the stellar material, creating waves and disturbances visible as those giant, uneven features. The most compelling clue, however, came from ultraviolet observations by the Hubble Space Telescope. They revealed a vast, arching shock wave plowing through the interstellar medium ahead of Betelgeuse as it moves. The shape and structure of this bow shock are complex, suggesting it might be shaped not by one star, but by two, their combined stellar winds colliding and sculpting the gas in unique ways. So what could this hidden companion be? Speculation points toward a small, hot star, perhaps a white dwarf or even a main sequence star trapped in a close orbit. Betelgeuse itself is so immense that if placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Within that staggering volume, a smaller star could easily be concealed. It would be hidden first by the sheer, blinding glare of the supergiant's luminous disk, but more effectively, it would be shrouded by Betelgeuse's own dusty envelope. Red supergiants are prolific dust factories, constantly shedding their outer layers in great, cool winds. This creates a permanent, opaque veil of microscopic grains around the star. A companion orbiting within or just outside this dusty shroud would be completely obscured, its light absorbed and scattered before it could ever reach our telescopes. We would only sense its presence through the gravitational ripples it creates on its giant host, like listening for the footsteps of a ghost in a hall of mirrors. The potential existence of this companion adds a thrilling layer of danger to Betelgeuse's inevitable supernova. A close orbiting partner could influence the explosion's mechanics, potentially altering the brightness, the asymmetry of the blast, or even the properties of the remnant it leaves behind. It transforms the star from a solitary, dying giant into a binary system facing a cataclysmic divorce, where one star's death throes will violently engulf the other. The companion to Betelgeuse remains a hypothesis, a shadow within a shadow, but it exemplifies a profound truth in our search for hidden stars. Sometimes the most massive and obvious beacons in our sky are the perfect cloaks for their own deepest secrets. Galaxies within a cluster wage a silent, gravitational war. As these immense islands of stars swing past each other in their slow cosmic dance, they do not simply pass untouched. They steal from one another. The outermost stars of each galaxy, those loosely bound in its distant halo, are vulnerable. During a close encounter, the rival galaxy's gravity can reach in and pluck them away like a giant's hand sweeping through a swarm of fireflies. These stolen stars do not fall into the new galaxy. Instead, they are flung into the abyss between them, into the vast, hot ocean of gas known as the intracluster medium. Here, they become permanent exiles, stars without a galactic home. They drift alone in the immense darkness between the brilliant island cities of the cluster. Their numbers are staggering. In a massive cluster like the Virgo or Coma cluster, as much as half of all the starlight may come not from the galaxies themselves, but from this sea of lost suns. Trillions of individual stars adrift in the intergalactic void. Yet seeing even a single one is nearly impossible. They are not clustered together. They are spread across millions of light-years of empty space, creating a population so diffuse it is the very definition of sparse. From our vantage point, the combined light of these countless exiles creates only the faintest possible background haze, a ghostly glow that permeates the space between the galaxies. This intracluster light is so dim it is often 1,000 times fainter than the natural glow of Earth's own night sky. Detecting it requires extraordinary measures, pointing the world's most powerful telescopes at what appears to be empty black space between galaxies, and taking exposures for hours or even nights on end, slowly accumulating every precious photon. The resulting images are haunting. They reveal a soft, ethereal blue fog connecting the galaxies, a cosmic cobweb woven from stolen starlight. Within that fog, pinpointing a single intracluster star is like trying to identify one specific raindrop in a distant moonlit mist. Their isolation is absolute. Imagine the view from a planet orbiting such a star. Your night sky would be a profound and terrifying blackness, punctuated not by a band of Milky Way, but by the distant, receding smudges of entire galaxies. Your own sun, a solitary wanderer, would have been traveling this void for billions of years, a castaway from a galactic shore it can never return to. These stars are the ultimate cosmic refugees, their faint, collective whisper the only testament to the slow, relentless theft that shapes the universe's largest structures. Our own moon, the familiar guardian of our night, is a master of celestial concealment. As it journeys around our planet, its black disk glides silently across the starry backdrop, and any star lying directly in its path is suddenly, cleanly erased. This event is a lunar occultation, a perfect cosmic alignment where our satellite becomes a moving curtain, temporarily hiding a distant sun. For a few minutes or even seconds, the star vanishes, its light extinguished not by distance or dust, but by the stark, airless silhouette of the moon itself. This simple, predictable phenomenon became one of astronomy's most precise tools. Before the era of powerful telescopes and space-based interferometers, measuring the true diameter of a star was nearly impossible. Every star except our sun is so distant it appears as a mere point of light, its disk hopelessly blurred by Earth's turbulent atmosphere. The lunar occultation offered a solution with razor-sharp clarity. As the moon's leading edge approaches a star, astronomers would watch with stopwatches and sensitive photometers. The star does not wink out instantly. Because it has a tiny but real angular size, its light disappears over a few thousandths of a second as the moon's limb sweeps across it. By timing this disappearance with exquisite precision and knowing the moon's exact orbital speed, scientists could calculate the star's apparent diameter. It was like using the sharp edge of a coin to measure the width of a distant light bulb filament by timing how long it took to cover it. This method revealed the true scales of red giants and confirmed the astonishing compactness of white dwarfs. But the occultation's hidden power went beyond measuring sizes. Sometimes a star would not disappear in one smooth, quick fade. Instead, it would flicker, dipping in brightness several times in rapid succession just before vanishing. This was the signature of a secret. The target was not one star, but two, a close binary system so tight that no telescope of the time could resolve it. The moon's edge acted as a perfect moving slit, scanning across the double star system and revealing its dual nature through these telltale brightness dips. It was a discovery by Eclipse, using our moon as a celestial scalpel to dissect the light of a sun millions of times farther away. These stars, periodically hidden by our closest neighbor, remind us that the most profound revelations can come from the simplest shadows. The moon's silent transit creates a fleeting laboratory in the sky, turning an act of cosmic hiding into a moment of perfect, revealing clarity. The ultimate hidden star may not be a star at all in the conventional sense, but a new state of matter forged in the final, crushing moments of a supernova. This is the hypothetical quark star, an object so extreme it pushes the very definition of matter to the breaking point. We know that when a massive star dies, its core can collapse into a neutron star. In that state, the pressure is so immense that electrons are forced into protons, merging to form a solid ball of neutrons, a city-sized object with the density of an atomic nucleus. But what if the collapse does not stop there? What if the gravitational pressure becomes so overwhelming that even the neutrons themselves cannot hold their structure? Theory suggests that under these inconceivable conditions, the neutrons would shatter, their boundaries would dissolve, and their constituent particles, quarks, would be set free. Up quarks, down quarks, and strange quarks would no longer be confined within individual neutrons, but would mingle in a single, uniform soup. The entire star would become one gigantic nucleus of quark matter, a state physicists call strange matter. This quark star would be even smaller and denser than a neutron star, a perfect sphere of the universe's most fundamental ingredients. Its surface would be harder than diamond and smoother than any material we can imagine, a flawless boundary where the rules of particle physics govern reality. The challenge, of course, is that such an object would be the ultimate cosmic impersonator. From a distance, it would look and behave almost exactly like a neutron star. It would spin, it might have magnetic poles that emit pulsar beams, and it would glow with residual heat. You could point every telescope in the world at it and swear you were looking at a normal, if incredibly dense, neutron star. Its hiding place is its own perfect disguise. The only way to unmask a quark star would be to take its most intimate measurements. Astronomers would need to determine its mass and its radius with extraordinary precision. The telltale sign would be in the numbers. For a given mass, a quark star would be slightly smaller than a neutron star. That difference might be only a few miles, but in the equations of extreme physics, those few miles are everything. It is the difference between a ball of crushed neutrons and a ball of pure quark essence. Some of the most massive, compact neutron stars ever found, like PSRJ 0740 plus 6620, hover right at the theoretical limit of how dense matter can be before it collapses into a black hole. Could it be that these objects are not neutron stars at all, but have already crossed that threshold into the quark realm? They stand as cryptic candidates, their true identity locked within their impossible density. To confirm, one would be to peer beyond the neutron, to see the universe not as atoms or nuclei, but as a sea of its most basic building blocks. The quark star represents the final frontier of hidden stellar corpses, a ghost in the machine of matter itself, waiting in the data for the moment we learn how to ask the right question. The hidden stars we have explored are not a single mystery, but a spectrum of cosmic concealment. They range from theoretical phantoms powered by dark matter to colossal giants shrouded in their own dusty birth clouds. Some are hidden by the overwhelming glare of a neighbor, others by the simple, profound geometry of our own vantage point in space and time. This incredible diversity reveals a fundamental truth about our universe. The cosmos is not merely the collection of lights we can see. It is a far richer, deeper, and more mysterious place, filled with wonders that operate just beyond the edge of our direct perception. The quest to find these hidden stars is not a side project in astronomy. It is the very engine that drives the science forward. Every new telescope, every clever observation technique, is an attempt to pull back another corner of the cosmic veil, to listen for whispers in the static of the void. This journey reminds us that knowing something exists even when we cannot see it expands our understanding of reality itself. So the next time you look up at the night sky, see it not just as a tapestry of familiar lights, but as a map filled with blank spaces, each one holding the promise of a discovery yet to be made. Which of these hidden stars captured your imagination the most? Was it the ancient drifting halo stars, the stellar vampire hidden in plain sight, or the theoretical quark star pushing the limits of matter itself? Let us know in the comments below.